Everyone. In this set of videos, we are going to move a bit away from the hardware side of things and start looking at the software. In particular, what we are going to do is to look at how the Linux operating system handles the concept of device drivers and essentially how it takes us from the idea of working with registers where we can communicate with our hardware to a file-based interface, which makes it more natural from the point of view of interfacing with software. So the objectives broadly, we are going to see how Linux exposes hardware in the form of files. So in other words, from the programmer's point of view, things look like files. At the back end, of course, it is studying some specialized kind of hardware that's running. And the bridge between these two works through memory mapped I/O, right, which we have been discussing about memory maps and the address spaces and so on. What we want to do is to understand how those memory mapped I/O registers get mapped through a kernel programming interface, the API, the application programming interface, into what's called the user space, right? And as a demo, I'll also be walking through how we can build and load a minimal device driver on any Linux PC. And this is something that you can actually try out. And it just sort of gives you a feel for the fact that actually a device driver may not be as complicated as it sounds at first. Of course, what we'll be doing is something extremely trivial, but still, it gets us started with that. Now, along the way, I'll be using a lot of terms that are related to operating system, terminology, background, and so on. But I want to sort of emphasize once again that this course is not going to be sufficient to really understand what an operating system does, right? The main focus here is going to be on the device driver side of things, and that too primarily on functionality. Later on, we will take a little bit of a look at performance. But in order to really get good drivers, in order to understand the full impact of what it is that we are trying to do, you need to have a lot more background in terms of what happens within an operating system. Some of the terms, including concurrency related issues that come up, I will be just sort of mentioning without really explaining them in much detail, because as I've mentioned earlier, an operating systems course is a full semester long course in itself. And it would be worth it if you are diving deeper into how exactly an operating system works and how it interfaces with hardware. We are going to be focusing only on the very minimal part that that is required in order to understand how devices can interact with the software, the operating system. So let's get started right at the beginning. In other words, what do I mean by right at the beginning? What happens when you switch on a computer, right? This is essentially what we normally call system power on. And of course, the first thing that happens with any digital circuit, not just a CPU, is we assume, especially if it's a sequential circuit or rather only for sequential circuits, that there is a concept of something called a reset. So what does a reset do? It essentially says that there are storage elements present inside your circuit. Those are, of course, our flip-flops. It could be some memory blocks, but primarily we are interested in the flip-flops. And to be more specific, we are primarily interested in those flip-flops which hold information related to the state of the system. Now, what do I mean by that? After all, isn't every flip-flop holding something related to the state of the system? In principle, yes, but I could also argue that the memory, the megabytes and gigabytes of RAM that are present in the system don't really contribute anything meaningful to the state of the system as such, especially at boot up time, right? On the other hand, things like, for example, the program counter, the state of some of the internal registers, those are directly related to the state of the processor. And in fact, they directly influence what's going to happen next when the processor sort of switches on and then the clock starts ticking from that point onwards. So coming back to our system power on, we have just switched on the system. A reset has been applied and all the state related registers have now been reset to known values, not necessarily to 0, just to some known values. In particular, the most important of those registers is the program counter, right? And this program counter is loaded with a default value. Note that I'm not saying that default value is necessarily 0. It could be, it need not be, right? And in fact, for things like the x86 class of processors, typically the default PC on switching on the system is not 0, right? It will be some other value. because the assumption is that whatever you want the system to do at that point is going to be loaded into that location in memory. And that's really all that you need. Now, let's think about what happens the moment that the PC has got a value, the program counter has got a value, and then the clock starts ticking, right? You get positive edges on the clock. From our understanding of how a CPU works, we know that what's going to happen is that it will start fetching instructions from the instruction memory, where in the instruction memory, the address corresponding to PC. Okay. So this fetching of instructions means that if I can set up my hardware in such a way that whatever is connected at the memory location corresponding to PC gives me back valid instructions, they will get executed. If it gives me back invalid instructions, the CPU will either it will go into an error state or it will ignore those and continue just incrementing PC, right? Depending on how the CPU has been built or designed, of course. So let's assume that somehow, once again, I have managed to set up my hardware in such a way that the very first address generated by PC corresponds to a location that when I try fetching an instruction from there, gives me back valid instructions. Now that ultimately, when you switch on your computer, you might have come across this term BIOS, the basic input-output system. What happens is the manufacturer, the person actually building the CPU board for you, the motherboard, is going to put in some set of instructions and wire up your entire processor and everything else in such a way that when that address corresponding to the default PC comes out, it's going to come back with instructions corresponding to the BIOS, right? So this is in the manufacturer's control. You can decide that I'm going to connect up the wires on my chip and on my board in such a way that the default address that comes out is going to get a response, which is going to be valid instructions. Now, typically that's going to be a very small set of instructions because, like I said, you don't have much space to store a whole lot of information. But the good thing about programs is that you always have instructions like jump, which allow you to basically jump to portions of memory that can have much larger storage, right? So the BIOS might itself be something in the flash memory of the CPU of the motherboard, which has a very limited amount of information. But all that it needs to do is to contain some extra functionality, which tells the CPU how to activate, let's say, a disk. And from the disk, to load large amounts of data into RAM and then jump to that part. Now, this entire process is called bootstrapping, right? Because it's related to essentially a story about pulling oneself up by one's bootstraps and how you could basically fly by those means, right? The reason why this is done is because if you think about this process, it's sort of, there's something circular happening out here. I cannot really load a program until I have a device driver that knows how to get information out of the disk and into memory. So where do I start, right? And this default value of PC, the flash memory, which is built by the motherboard manufacturer and put in place, basically the BIOS, all of those put together help us to do this bootstrapping process. Okay? Now, what that means is that for, let's say, an embedded microcontroller, an Arduino or whatever it is, the program that you have got, you wrote a program in, let's say, in the Arduino IDE, you compiled it into a binary file, and you somehow managed to flash it into the memory of the microcontroller, right? What happens over there is precisely the same thing. The program is actually getting loaded into a portion of memory that will respond corresponding to what happens when you get out of reset. Which means that when I then sort of power on the microcontroller and sort of take it out of reset, it's going to start executing those instructions. Which is perfect because this is essentially what's called a bare metal execution, right? I have a processor, I have a small PCB built around it, I have some memory. The program that I want is directly aware of everything that the processor can see. Every connection, every peripheral is known to the program, and the program has to then decide how to interact with it. If you want a timer, the program needs to go and set values in the registers and so on. So this is sort of the default mode in which systems operate, right? You have a processor, you have a motherboard, you have some program in memory. That's called bare metal operation. Now, you can probably already imagine that, this is very limited, right? What happens is all the functionality that you want has to be baked into this basic system. If you wanted to communicate with a serial port, the driver corresponding to a serial port, or all the register functions to talk to the registers in the UART interface need to be declared in your program and compiled in. In general, it does not have a concept of multitasking, right, or time multiplexing between different tasks. If at all you want to have 2 different things or 3 different things being processed by the same thing, you need to be explicit about it. You would probably have some kind of a while loop. Even if you go for some kind of a basic operating system, right? Like we considered the FreeRTOS and so on, right? All that is doing is providing you with some kind of a while loop that basically says, okay, this program will run for a certain amount of time, then stop and hand over to another function. So the functions basically switch from one to the other individually. You have to have the full control over that. Now, as an alternative, what people realized was as computers get more complicated, right, more complex, and they are capable of doing more things, it's pretty much impossible to do this sort of, fine-grained control at every step of the process. So instead of that, let's say that the very first program that runs after the system comes on is going to be a special program. It's not going to be a browser. It's not going to help you check email. It's not going to, help you draw things on the screen. What it does is that it will take over the functioning of the system and provide facilities to other programs. That includes the ability to, for example, load other programs that have been stored somewhere, maybe on disk, into parts of memory, jump to those instructions, execute those instructions, wait for that program to give control back, or take control from the program by just interrupting it when necessary, right? All of that is the work of the very first program that gets run after the system reset. That program, in the context of the Linux OS, it's usually called the init program, is the very first program, of course, and that is sort of the core of your operating system. The operating system itself is more than that. It provides a lot of different kinds of facilities and features, which other programs can then make use of. Right? At a very high level, this is the kind of stuff that an operating system does. It handles something called process scheduling, which basically decides that, okay, there are multiple programs you are trying to run, or multiple processes to be more accurate, right? Normally, when we are interacting with a system, I might say that, I have, for example, a PDF reader open right now, which is showing these slides. There is a browser running somewhere which has a couple of web pages open. There are maybe some other programs, for example, there's something that would show me a clock on the screen if I was to see the desktop, right? And of course, there is also something that is handling any keyboard events, right? I press something on the keyboard or I write something with the mouse or the stylus. All of that needs to be responded to. The way that modern operating systems work is pretty much each of those functionalities is split out as different processes, which means that the operating system now needs to decide which process needs to execute at what point in time. Now, there is a certain amount of memory available with the system. When you buy a laptop, for example, you might see that it has 8 GB of RAM. Okay, what does that mean? It means that 8 GB is physically connected somewhere. Now, does the operating system just take over all that 8 GB and say, yes, I have all of this memory, I can use it any way I want? Or does it say, okay, there are different programs that need to run. Let me sort of give each program the amount of memory that it needs and keep the rest available so that as and when new programs need to be started, they will be given memory. And as and when a program finishes, I can reclaim that memory and then assign it to someone else. So that memory management is one of the most important functions of the operating system. Apart from that, it also handles storage, right, and file systems. Now, technically, storage is also a form of memory, except that it is qualitatively different, right? And you can clearly see that storing something to disk, you don't just sort of assign an address to some place on a disk and say, okay, I'm storing it at this address location. You actually have a different way of organizing things. You assign files, directories, file names, and you use a completely different interface in order to interact with data that is stored on the disk. The entire computer also contains a lot of input-output devices, right? The keyboard, the mouse, the video display, the screen, and all of those in turn require drivers, right? You need to have direct memory access, which allows you to copy data between parts of the system memory and maybe the video memory in order to display something on the screen. Let's say that you have a high-speed Ethernet card and large amounts of data are being received. There has to be a DMA engine that takes care of taking that data and storing it somewhere in memory and so on. Similarly, networking, also a form of I/O, but important enough that it probably merits a sort of separate class in itself, right? The whole how do you communicate with other systems is a sufficiently complicated thing that there is an entire portion of the operating system devoted to handling network. And one of the most important things that an operating system handles is in the context of security. Right? Now, why do we need security? Of course, you are probably familiar with the idea that a virus can infect your computer. You have Trojans, you have various kinds of so-called hacking attempts and so on that people can make in order to try and break into someone else's computer. The point is all of that arises from the fact that if you have two processes that are running on a computer, they are not running at the same time. They are time multiplexed. So one of them runs for a short amount of time, it switches over to the other, then switches back and so on, fast enough that you can't really tell the difference. But what that means is I don't really want one of those programs to be able to know what the other one is doing, because I cannot guarantee that both were written with the same degree of privacy concerns and security issues, security care abouts as the other ones that I might be interested in, right? I might, for example, be writing a document which contains information that I do not want someone else to see. And I do not want the web browser which is running in the background to be able to read that information and sort of email it or send it somewhere else, right? So each and every process needs to get isolated from the others. And a large part of what a modern operating system does is handling that security, these security aspects in a sort of robust manner. Now, as you can see, there are a lot of things that an operating system does. We are going to focus only on the driver side of the I/O stack. So pretty much just one small corner out here, right? And even here, we will spend most of our time understanding the basics of drivers. And we'll be talking about things like DMA and interrupts and power management and so on, but not really going too deep into them because unless, as and when we can get to the point where we will be talking about them only in the context of specific drivers that we are going to consider. But the rest of the things, so for example, some amount of how does memory get managed and what are the issues that we need to deal with in terms of security especially, these are things which you need a little bit of background knowledge of in order to fully appreciate why certain drivers are written in a certain way or what are the limitations that come when you try to implement a driver, right? I will be bringing in only those aspects of memory management and security that are required in order to understand their impact on drivers. I will not be talking about the details of how we go about doing memory management in a modern OS. Right? That's beyond the scope of what we can cover here.